The analysis of geomaterials, in particular soils in the context of this series, is always intimately related with gravimetric and volumetric parameters. Today we are going to explore them, and I would also like to take you a step further to show some of the relationships that appear systematically throughout the literature. So let's start with volumetric relationships. The one that is most commonly used throughout the engineering and scientific literature is the porosity, defined as volume of voids over the total volume of the material. There is a problem with this relationship, and in our community we have been very wise to create a complementary definition. The reason is that there may be some soils that have a very large volume of voids with respect to the total volume. For example, Mexico City soils can have 95% of the volume of the sediments beneath the city can be voids. And so we would like to stretch the scale a little bit more, because this scale goes from zero volume of voids, a solid material like precipitated salt, over the volume total. So this goes from 0, and it could end up at 1, but it cannot go further. So in our community we have defined another parameter, which is the void ratio, which is defined as, this is what I mean by the three equal signs, 3 lines, meaning by definition, this is the volume of voids over the volume of the minerals. We also have to think of one more definition. If we have a soil which has many particles, and then water may be forming in the form of capillary menisci, then we have to wonder how much of the volume of voids is the water occupying. If water occupies the whole volume, then there will be one behavior, for example, for liquefaction. However, if gas is inside, it becomes very compressible. So this is an important quantity, and we're going to call the degree of saturation, which by definition is the volume of water, if it is the degree of saturation for water, divided the volume of voids. Similar expressions could apply, for example, if you have contaminants, a D-napole or an L-napole, or if you are in the oil industry and this is the volume of oil and water. So you have to specify which is the species, the species that you are addressing. So these are volumetric quantities. We should also look at quantities that depend on mass, and probably the most important one that we are going to define is the water content, which by definition is the mass of water over the mass of minerals. Finally, there are some definitions that involve both mass and volume, and the most critical ones, of course, is mass density, which by definition is mass over volume, or the unit weight, which by definition is the weight over the volume. In many cases, we do not want to carry all these definitions, and sometimes we are going to normalize. For example, we are going to define the specific gravity as the mass density of the material that we are looking into divided the mass density of water, which happens to be the same, multiplying numerator and denominator times gravity, is going to be the same as the unit weight of the quantity divided the unit weight of water. Please notice that I am not using percentages because it gets confusing. We don't need to include percentages in the definition of the degree of saturation or in the definition of water content. This is what they are. Whether it is a 0.3, it's not 30%. Once again, to avoid confusion and for the rest of analytical derivations, the form of these definitions, it is indeed much more convenient. Phase relations are interrelated among themselves. Therefore, we're going to explore today 4 or 5 of those typical associations that we may find throughout the geotechnical literature. The first one and most important is how is porosity and void ratio, how are they related? So we start with the quantity that we are going to transform by its own definition, which is the volume of voids over the volume of minerals. And we are going to gradually mutate it until we reach the definition of porosity, which is the volume of voids over the total volume. Now, please notice that the volume of voids appears, but is not the volume total. This is the volume of minerals, but we realize that the volume of minerals is equal to the volume total minus the volume of voids. Therefore, now if I divide numerator and denominator by the volume total, I get volume of voids divided volume total over 1 minus volume of voids divided volume total, which is equal to porosity over 1 minus porosity. This methodology that we have just described, which is we start with the quantity that we know and its definition, and we gradually evolve it until we can express it in terms of the other quantities, is the standard methodology that we should follow in relating all these quantities. There is an expression that appears very often in our results, and it is very convenient to convert quantities, and is the following. By the way, you can think of the following simple expression to remember it. Gravity waves are caused by supernova explosions. And so, GW equal SE. Instead of following the protocol that we developed above, now what we can do is we can transform this and see where this one takes us. And this is G times water content by definition was the mass of water over the mass of mineral, is equal to degree of saturation is the volume of water over the volume of voids, and void ratio is the volume of voids over the volume of minerals. Therefore, this cancels out, and if I divide now, I bring mass of water to the denominator here and the mass of mineral to the numerator, I get that G is equal to the mass of mineral divided the volume of mineral, and the mass of water divided the volume of water, which is equal to the mass density of the mineral with respect to the mass density of water, which indeed is the specific gravity of minerals. So this is confirmed. There are other expressions that are quite convenient. Let's explore the following one. In another meeting, we talked about the specific surface area of platy particles like clays. where this was L, and this is the thickness, much smaller than the length, and so the specific surface area was equal to 2L squares over L squared T times the mineral mass density, which cancels out to become 2 over the thickness of the particle times the raw mineral. Now let's take this one step further, and by definition of void ratio, if these particles are infinitely long and they are of thickness T, and there is a gap between these two, which is more or less the size of the pores, then we can say that for this configuration, and of course it repeats above and below, this is a repetitive structure, this would be a dispersed clay. For this configuration, void ratio, which by definition is the volume of voids over the volume of minerals, becomes the volume of voids is dp, which is the thickness of the void times L squared, divided the volume of the minerals, which is L squared times T. The L squared cancels out, and we have that the void ratio can be a ratio between the pore size and the thickness of particles. But we realize that the thickness of particles is captured in the specific surface, which is quite easy to measure. And so the thickness of the particle is going to be equal to 2 over the specific surface times the raw mineral. So if I replace in this equation now, this is the pore diameter divided the thickness of the particle, which is 2 times specific surface raw mineral. Therefore, I can estimate the mean pore size distribution by knowing the void ratio and the specific surface of the material. This is a very convenient relationship because it is very difficult to estimate the pore size, for example, in clays. Many people have attempted to do freeze drying and to observe under a scanning electron microscope, which gives you a flat perspective. So these are always very difficult measurements to make. However, if you can measure the specific surface, once again, it's very easy by colorimetry, and the void ratio, which is the soil is saturated, you get it from the water content, then you can have an estimate of the mean pore diameter, and that will have lots of implications, such as the viability of life, microorganisms within soils. Phase relations appear whenever we deal with mixtures. That would be the case if you have a soil, water, and air, soil, water, and organic contaminant, or oil in the subsurface. They also appear, for example, in concrete mixtures. How much coarse aggregate, fine aggregate, and Portland cement paste we need. So let's see how some of these relations appear all together, and you will see the pattern in many other examples throughout your professional experience. So let's start by thinking that we have a soil mass which may have some parts of this with water, and the rest, let's say, that an organic phase. So this is the mineral, we have the organic phase, and this is water. And we would like to know the mass density of this mixture. Therefore, we start by our question, which is, what is the mixture mass density, which is going to be the mass total over the volume total? I shall take it shorter so we don't carry so many subindices. And this is the total mass density of the system. Now, in this phase, in this mixture, we have the mass of the mineral phase plus the mass of the water phase plus the mass of anything else, could be air, could be an organic contaminant, let's say O, over the volume total. Now, we can replace each of these masses by their corresponding mass densities and volumes. And so this is going to be the mass density of mineral times the volume of the mineral plus the mass density of water times the volume of water plus the mass density of the organic component times the volume of the organic component divided the total volume of the system. Now, these two volumes are the volume of voids, and this is the volume of the mineral phase. So the volume of the mineral phase is equal to the volume total minus the volume of voids. Therefore, I'm going to begin making some replacements. This is going to be equal to the rho of the mineral phase, and now I distribute the volume total, and it's 1 minus the porosity. Now, on the other hand, the volume of voids over the volume total is the porosity, but the problem is that it's the sum of these two. So what is the volume of water with respect to the total volume of voids? That is the degree of saturation. So this is going to be plus rho water times the degree of saturation times the volume of voids divided the volume total plus rho organic matter is the complement of the degree of saturation, which is 1 minus the degree of saturation times the volume of voids over the volume total. Therefore, my final equation is rho mineral 1 minus the porosity plus I can factor out this quantity becomes the porosity, and this quantity is the porosity as well. I can factor it out. Porosity times rho water, saturation of water, plus rho organic matter, 1 minus the saturation of water. This type of formulation indeed appears quite often when we're doing mixtures where the porosity and the degree of saturation of one of the phases in the pores are involved. To conclude this section, let me leave you with an assignment. Imagine that we have a granular packing, and this is the coarse phase. So there is a coarse fabric of grains, but inside it there are also finer grains. If I zoom in to the arrangement of the finer grains, I conclude that it doesn't have to be fine, I'm going to call it finer, that the finer grains in that narrow region here is packed at the void ratio of fines, and it has its own mineral mass density for the fines, and that the coarse, if I forget about the presence of the fines, it will be packed at the void ratio for the coarse, and it has a mineral mass density that corresponds to the coarse. So I have a question for you. Can you determine a relationship of their mass fraction? How much mass of fines is there with respect to the total mass of the soil. In other words, I'm asking what is the relative amount of mass of fines with respect to the mass of the cores plus the mass of the fines, and I'm just using the F just to avoid carrying too many subscripts. This will be very important because this will allow me to define a new soil classification method that will properly capture how much fines, the relative mass of fines, that will gain control on the behavior of the soil mass. We will come back to this.